So this will happen. Suppose here 1 and 2. We have an equation like that. So what is happening here? So this value, how do you get it? 1, 2, 1, 2 divided by 2, which is 0. How do you get it? 1, 2, 1, 2 divided by 2, which is 0. So if you have 0, also here it is 0, then we cannot calculate because later on here it will be 0. Something by 0, undefined, infinity, right? Something by 0 is undefined. So we cannot use this. So we need to replace it. How do we replace it? We need to consider, we need to calculate one equation that is called auxiliary equation. So this auxiliary equation will be equal to, and find out the dq of that, derivatives of that equation equal to 0. Then we replace it. Replace that here. Now look at this. How do you do that? Here, this equation qs is equal to 2s4 here, 2s4, which is here. Then what? 2s squared, 2s squared, and then what? Plus 2. We need to write down the equation. We need to solve this equation. How do you solve it? We take the derivatives. dq s by ds is equal to 8s cubed 4s plus 0. Then this one should be equal 8s cubed plus 4s. Now here we can take this common. What? 4. We take 4 common and we put it in this side. So we can write it 2s cubed plus s equal to 0. But we cannot take this s. We cannot take this out as s. Why? Because s we need this because it is the board. So we cannot take it out. So now here we have the value 2s cubed plus s. Now we have the coefficient, the root 2 and 1. 2 and 1. That's how we solve this. Now we don't have any 0 here. So what do we do? First we write an equation. Name it qs. 2s4, 2s squared plus 2. Then we take the derivatives of that, and if you do the derivatives of this equation, then we have this 8x s cubed plus 4s plus 0. And this equation dqs by ds has to be 0. We already know that in our previous slide. So this we solved it and we find out the root. Now this one. Now you calculate, you form the whole table. How do you do that? Here 2, 2, 2, 2, 2, 1 divided by 2, which is 2 minus 4. 2 minus 4, that is minus 2. We have minus again, plus 2, 1. Here, this one, 2, 2. Then what? We have this is 0. If there is no value, that is 0. 2, 0. Divided by what? 2. So 0 minus 4, that is minus 4 into minus plus 4, 2 divided by 2 equal to 2. This one 2, 1. This is 2, 1 and 1 divided by 1. So 4 minus 1, that is 3 minus 3, and here it is 0, right? Here, so it is 0, and then it will be 0. And then this one we will calculate it again. So we have 1 and minus 3. 1 minus 3. Then what? 2, 0. Divided by minus 3. So 0 plus 6. And 0 plus 6. It will be minus 6. Minus 6 divided by minus 3. Plus 2. So now check plus, 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 minus, plus. So here 2 sign change. That is unstable system. Because 2 sign changes. So this is another example. Okay, now we will talk about the steady state error. We completed the Routh-Hurwitz criteria. We have one topic. This is another topic. Steady state error. What is a steady state error? In a system like here, we have an RS in the system having a feedback HS, GS. We know that. Now here we have error term. Error. This error. This is called steady state error. Shortly we call it SSE. This is the steady state. What is that? It is a comparison between reference and feedback. Comparison between reference and feedback. Reference and feedback. This is feedback. This is feedback. HS. So we know already that CS by RS is equal to what? GS 1. This is minus plus GS HS. That is a transfer function. Now here, any physical control system inherently suffers steady state error. Any control system. That means here there will be some value. Now if steady state error is equal to 0, 0, that means what? No error. No error. 0 means no error. That means what? Your system is stable and highly accurate. If steady state error is 0, that means your system is stable system and highly accurate system, no error. So, but how can you determine this steady state error? Here, this error actually it respond for this different types of input. This RS, suppose here this RS can be anything. Suppose this can be this delta T RS or UT or RAM RT or parabolic PT. Any four. This RS can be any. So it will respond based on different types of input. If suppose there is no steady state error for a step input, it will show an error for another type of input like ramp input. So this steady state error mostly depends on the open loop transfer function, this transfer function. for a given type of input depends on the open loop transfer function. Now we need to find out here the first order system. We know that with a 0 we can write it k by 1 plus alpha s ts plus 1. This is our first order transfer function. K by 1 plus, this is a 0 and this is 4. So in numerator we have 0 and in denominator we have 4. Now if we expand the equation, number of zeros, number of poles. So TS plus 1, TBS plus 1, these are all zeros and these are all poles. Okay, I'm just expanding this equation. These are zeros and these are poles. Number of zeros, number of poles. So we are just expanding it M and P. Here we have only one, here we are expanding it. Now look here. There is one term that is called Sn, S power n. This n is the system order. Here. Is n in the denominator, it represents n pole of at the origin, n poles. So we know that what is the n pole of the origin? Look. Here, this is origin 0 0. Sn. Define that how many poles at the origin. This is origin. Sn. N is the number of poles in the origin. So n equal to 1, 1 pole. N equal to 0, 0 pole. N equal to 2, 2 pole at the origin here. So a system is called type 0, type 1 and type 2 if n equal to 0, 1, 2. For n equal to 0, the system is called type 0. N equal to 1, type 1. N equal to 2, type 2. And n equal to 3, type 3. So n defines the type of system. We need to understand the type of system. We will need to deal with that. Now we know that already. If a system, if the type number increased, like type 1, type 2, type 3, accuracy is improved. Higher order system accuracy is improved. But however, increasing the type number, it will decrease the stability. So there is an inverse relation. The inverse relation. If the type number increase, accuracy improved. But if type number increase, stability decreases. So you must need to maintain a balance between these two, accuracy and stability. Look, I wrote stability and accuracy. We must need to make a balance between these two. So we need to calculate this. How do you calculate? We can calculate it by using steady state error. Calculating the steady state error. This is the transfer function Cs by Rs, Gs 1 plus Gs. Why it is Gs? Because here it is Hs. Hs equal to 1. It's 1. That's right. So it is 1 plus Gs and plus because of the minus. So here, this term, here we have an error. So this one we call it ES. Error term, ES. So we can find out this ES. By using 1 by 1 plus GS. Here, HS. 1 by 1 plus GS HS. Here, in this example, HS equal to 1. So we are just writing 1 by 1 plus GS. What is HS? There is a value, so you can write it 1 plus GS HS. How do you consider this 1 plus GS? So here we will apply a final value theory. Final value theory, that is final value and initial value. There are two theories. Final value is infinity. T does to infinity. That is called the final value theory. So this ES, the RS will be in that side. If we want to find out ES, because ES is the steady state error. This is what we need to find. ES. So ES equal to 1 plus 1 by GS into RS. Now RS can be any. RS can be any. So here, this delta S is what? 1. US is equal to 1 by S. RS is equal to 1 by S square. Then PS is equal to 1 by S cube. We already know that. We already have seen that, right? All the Laplace transform function, if we convert all the t into S domain, then we have this delta S 1, US 1 by S, RS 1 by S square, PS 1 by S cube. Here, you put this on the RS for the different input. Okay, now final value theory, it is t tends to infinity in limit of e t. Convert it in S domain, because time domain we cannot do the analysis. If we convert it in S domain, then it will be S tends to 0, S into ES. We will have an S term. S into ES. Put this value here. SRS 1 plus GS. So now this is your equation to calculate error, steady state error. We will use this equation to calculate the steady state error. So to calculate the steady state error, we need to know about different constant value that are called the static error constant. So what are these static error constant? Let me tell you in details about this static error constant. Suppose I am having a spring. This spring x1 to x2, it is expanded. We know if the force applied, there will be a displacement. That displacement we call it del x. Displacement we call it del x. So in a given system, the output can be what? Changing position, displacement, changing position, or what? This is the changing position del x. So we call it displacement equal to what? Del x, or change of position del x. Now, if I want to find out the rate of change of position, rate of change of position, then what we need? We need to do dx by dt. That is what? That is called v, velocity. Rate of change of position, that is called v, velocity. V equal to dx dt, you know that. Now, if you want to find out rate of change of velocity, it is nothing but dv by dt. That is called acceleration, A. Now there are 3 outputs, not only one output. Rate of change of displacement, change of position, normal linear position. Rate of change of position, dx dt, that is velocity. Rate of change of velocity, dv by dt, that is acceleration. Now we have x, v, a, 3 output. Position, velocity, temperature, that is pressure or acceleration. Now, if there is 3 different types of output, then how can we define it mathematically? How can we define it mathematically, Routh? So if there is a temperature control system that changes the position, that means it changes the temperature, that is the changing position. We call it the output temperature. Position represents the output temperature. Velocity represents the rate of change of the output temperature. So these are the output in the thermometer. Normally we call them. So X and B. So we can define it by UT for this and this RT. So position change, we call it UT. We can consider that as UT. And rate of change of position. Rate of change of position, it is the velocity. Rate of change, dx dt. This is dx dt. This is x. This is y equal to x. Right? So the rate of change of position is dx dt. Now, also there is one more rate of change of velocity. This one, we can call it pt. That is what? T squared, right? T squared, which is t squared. Y equal to t squared. This is y equal to t. So y equal to t squared, y equal to t. T squared with 2. T squared with 2. Now let's do, if we apply the different input in the RS. Suppose here for this RS, let's apply a unit step. This unit step UT. So if there is, we apply an unit step, this UT is equal to 1 by S, we already know. So the RS will be 1 by S. RS is equal to 1 by S. So this S will be gone. Then we can call it 1 plus G0. How do you get it? I will show you. Look, this is limit as tends to 0, 1 by 1 plus Gs. So while you put S tends to 0 here, it is nothing but 1 plus G0. Put the limit of that S tends to 0, 0, 1 plus G0. So that steady position error constant Kp is defined by limit S tends to 0 Gs. This is the static error constant for the position. Static position error constant Kp. So put this as 0 here. You will get Z0. That means this value equal to Kp. That means here you can write in 1 plus Kp. This is your ESS steady state error. Now what is the value of Kp? You need to find out the value of Kp. How do you find value of Kp? We need to apply different type system, type 0, type 1 and type 2 to find the value. For the type 0 system, we have an equation. How do you find this equation? This equation I already showed you here. This equation, we will apply this equation. So here we have an S power n on the denominator, right? And K by Ts plus 1, Tbs plus 1, T1s plus 1, T2 plus, these are the zeros, this is the poles, this is the gain. This is the gain, K. And this is the type. This will determine the type. So for type 0, n equal to 0. So here this is S power n. Here n equal to 0 for type 0. So S power 0 is equal to 1. So this is equal to 1. That's why it is not written here. And now put this limit here as tends to 0, as tends to 0, 0, 0. If you put all the values 0, this will be 0, this will be 0, this will be 0, this will be 0. Only here there will be k. Only there will be k. So for the type 0 system, the value kp is equal to k. We are finding the kp value for the different type system. Now for type 1, n equal to 1. So Sn will be equal to S here 1, S1. So now put this S tends to 0 or S tends to 0. Now look at this. We have a value of 0 here. So this is k by 0. Something by 0 here. Something by 0. What do we call that? Infinity. Infinity. So once you find infinity, that means you don't need to do it. All the values will be infinity after that. All the higher order system will be infinity. Because type 1 you have infinity. Then type 2 here, n equal to 2. That means Sn equal to S squared. S squared here, S squared. Now again put S equal to n tends to 0, you will get infinity. Infinity. So for an unit step input, ESS is equal to 1 by 1 plus Kp. Here Kp is equal to K. And the second for type 0 is here 1 by 1 plus Kp. Here Kp is infinity. 1 by 1 plus infinity, that is 1 by infinity, that is 0. Something by infinity is 0. So this, what is this? What does it mean? What does it mean? No steady state error. No error. That means no steady state error. What does it mean? The system is stable and highly accurate, right? The system is stable and highly accurate. SSE is 0 means no steady state error. That means the system is stable and highly accurate. So you can determine the accuracy of the system by finding steady state error by using static error constant. This is only for Kp. And for the Kp, we need to use the unit step. Now we will find out for this Kv, static velocity error constant. Now for the Kv, which input? For V, which input? RT, ramp input. And ramp input, what is the ramp input? 1 by S squared. Here, 1 by S squared. So Rs will change. Now the input will change. So if Rs is S squared, then what will happen? Look, this will be S. So it is limit S tends to 1 to S. But how do you get it? Look, this is nothing but limit S tends to 0. 1 by S into 1 plus GS. Now here, put the limit of here. This one you can write it 1 by S plus SGS. This S will be 0. If you put the limit, S will be 0. Plus SGS. Here you cannot put S0 because something like 0 will be infinity. And we have a transfer function here. So you keep it. And this one will be 0. So we can write it limit S tends to 0. Only 1 by SGS. This one will be 0. So we don't need to write it. That's why we have SGS. Now static velocity error constant is defined by this limit s to 0 as gs. So this is kb. So we can write it 1 by kb. Now, what's the value of kb? We need to find the value of kb by using different types of system. Type 0. Now look at these, the differences. Here we have an s. Before there is no s. Why? Because of this equation. This equation there is no s. Here 1 by kb, here we have an s, sgs, sgs. And why it is s? Because it is differentiation. Differentiation. If there is a differentiation, if you differentiate and convert it in a Laplace domain, you will have an s term. So because of the derivatives, we have an s. So that's why we have an s here. Limit s gs. So this is the gs value. So again, we need to calculate it one by one. So first, put s. All the s value is 0. I'll put all the s value is 0, which is 0, right? Because we have an s term multiplied by all, it is 0. So why this is 1? Sn. Here n equal to 0. This is s0 equal to 1. This is type 0 system. Here Sn. Here n equal to 1. So this is s. Here now we have an s. So and also we have an s. This s and this s will be gone. Now it will not be 0. So put all the s 0. Limit is 0, 0. We have a k, so the value will be k. Now for type 2, n equal to 2, Sn equal to s squared. Here, s squared will be s, 1 by s. So now put s, all the s, 0, 0, 0. Here, the denominator 0, infinity, infinity. So once you find infinity, you don't need to do it because the rest of the type, higher order type, will be infinity. So that's why it is written type 2 or higher system, all the values are infinity. Now you have the value of kb. Now put all this value here, here, 1 by kb. So here we have the value. So this kb is 0 before, something like 0 is infinity. Then this kb is k for type 1. And then this one is infinity. Then it is 0. We know that. So for type 0 system, infinite error, very high error. Type 1 system, for RAM signal, finite input, finite error. And for type 2 or higher system, no error. So if we have a RAM input, then there will be no error for type 2 or higher system. Type 2 or higher system. But for type 0 and type 1, there will be error. Next is the Ka, that's acceleration, static acceleration. We use for the acceleration, it is a parabolic input, parabolic. So for the parabolic input, our input is 1 by s cube. So here the parabolic input it is 1 by s cube. So here this is s squared. So we have an s squared term now. And this term we call it Ka. So we can write it ES equal to 1 by Ka. So how do you find the K? Again, put the value for each. Now here our transfer function, there will be an s square term. For type 0, here s square. So here we have an s square because of this, and here it is Sn, n equal to 0, Sn equal to S0, this is 1, so it is 0, which is 1. So here 0, 0, 0, 0. So we have an s square, this is also 0, so this will be 0. Second one, Sn, this n equal to 1, so it is S1, this is S. So here we have 1. So this will give S again S. So put the limit. This S, put the limit. Here we have it 0 values, again 0. Next, Sn, here n equal to 2 for type 2. So it is s squared. Here, s squared, gone. Now it will not be 0. Because this s term is gone. So put s. All the value is 0, we have a k. So it is k. Finite. It is a finite value. Now Sn. N equal to 3. S cube. S cube. This is cube. We have an s squared. This is s. Now there is a term s. Now if you have 0, 0, 0, 0, put the limit. Now something by 0, here you will get an infinity. You need to calculate till you reach infinity. You need to calculate type 0, type 1, type 2, type 3, type 4, type 5 till you get infinity. Once you get infinity, then you don't need to calculate. So for type 0 and type 1, what is the value? We have this. This is nothing but 1 by Ka. So this is 1 by 0, which is infinity. Both for type 0 and type 1. And then this is 1 by Ka, which is 1 by K for type 2. And here it is 1 by Ka, which is something by infinity is equal to 0. So now here, no SSE for type 3 or higher system for parabolic input. For parabolic input, no SSE. That means for the parabolic input, type 3 and higher system will show no steady state error, no error for type 3 and higher system. Here is a summary for each one. You can read it. We already discussed that. I will discuss one example. So this is one example. What are the example? Example is finding the static error constant for this GS, open loop transfer function. So we need to find Kp, Kb, and K for the three different inputs. What is the input? Step, ramp, parabolic. This step, ramp, parabolic for the three inputs. So how do you find it? Kp is, the definition is limit as tends to 0 GS. Here we are using what? We are using step input. That's why no S. So here if you put S, it tends to 0. This is your full equation. As tends to 0, 0. If you put that, you have a 0, something by 0 gives you value infinity, infinity. Second, limit as tends to SGS. Now, because that is Kb, in the Kb we have the S. So now here we have an S. Again here we have an S. Again it will be infinity. And now next one is s squared gs, that is acceleration for steady acceleration constant. Now this s square and s square will be gone. This will be gone. So we will have a finite value. Finite value 10.4. So you know that how can you calculate the Kp. So you need to remember these equations. I showed you how you find it, but you don't need to do it. You remember these equations. For static error position, static error, position error, we have static position. We use 1 by 1 plus Kp. So here, this is 1 by 1 plus infinity. 1 by infinity, 0. Again, here 1 by Kb is infinity, 0. Then again, 1 by K, 10.4, which is 109. Finite value. So look, what does this information provide? The system, this system, what system? This system. This is the system, right? This is the system. This system shows no error for unit step input here. Unit step input, no error. Ramp input, no error. But for the parabolic input, it will have an error. So same system, if you use same system for the different input, it will respond differently. Maybe for one input there will be no error, for another input it will be error, there will be an error. So the steady state error will be depends on which type of system you are using and which type of input you are using. So depends on this different input, it will show error or no error. So you know how to calculate this. If you have any of these three input, you can calculate by using these equations. And you know how to calculate Kb, Kv and Ka by using this Gs, SGS and S squared Gs. That's how you calculate this. This is all about today's lecture. We talked details about the steady state error and Routh-Hurwitz criteria, which two very important topic for our control system.